Hi everyone, thank you so much for coming and witnessing to this presentation. Before I begin, I just want to spend just 2 words because the last 2 presentations are very similar to what we were presenting, and especially regarding EU regulations. I didn't put anything in this presentation, but yes, it is something very important, and each country is supposed to have their own rules when it comes to thresholds and limits for life cycle assessment and annual emissions. But it's something that still has not been reached everywhere, both in terms of policy and practices. With today's presentation, I want to give you an overlook of the current conditions, so common practices, common resources, and some advice for the future, so recommendation on how to improve the landscape. To start, this is table of content introduction. Why is it important to monitor CO₂ emission in construction? For a number of reasons. It is responsible for 21% of greenhouse gas emissions estimate. It also consumes 40% of available resources. It is something that is usually assessed using life cycle assessment, which despite being a very useful metric, it doesn't correctly display the actual activities being performed on the job site sometimes, because one thing is the planning and one thing is the execution. Sometimes delays or accidents may impact the time that is required and therefore how much emissions is produced by the machines on site. Because of this, there are big knowledge gaps in literature that we are trying to bridge and fill, and this is why we decided to invest time on this research. Specifically, idle time is something that we found to be very impactful in terms of emission, because idle time, as in the time where the engine is on but not working, consumes a lot of CO₂ without producing value for the construction site, and it is something that leaves plenty of room for improvement. Using machine learning models, we can use this data and others to predict emissions and trying to forecast rooms of improvement and trying to find where to actually intervene in the job site. So, methodology. To get the information needed, we use the Aarhus procedure to filter through all of the papers and literature on the subject, narrowing it down to only 19 papers published from 2019 onwards. Similarly, using the Delphi method, we consulted 4 different experts in the field to know more about this phenomenon. So, life cycle assessment expert, project management, IoT sensors, and an expert on European environmental regulations. Just a word on this. For example, in Denmark, where I'm based, I forgot to say, hi, I'm Patrick from Aarhus University, yes. And in Denmark, for example, there is a threshold of 1.5 kilometers of CO₂ by meter squared for each year during the construction. But in practice, none of the construction sites know of this and respect it. So, practices. Currently, most information used comes from historical records, usually either from machine transcript or employee themselves reporting the activities that they've done or how much machines has been used and so on. This is a good measurement, of course, but there are some limitations. For example, there is no validation of this information. It's unreliable. It does not capture the actual work being performed, and it does not also leave room for external information to be integrated. The solution that I propose today with my team is to integrate real-time monitoring using Construction 4.0 technologies with project status information, which could be life cycle assessment, schedule, progress updates, and so on. In terms of advancements in the present, for these 2 fields, we have many tools that we can access. Digital twin, BIM, IoT sensors, project updates, schedule, and so on. Combining them represents a good way to improve the measurements, and it has downsides and upsides. When it comes to pros, it is easily scalable, it provides accurate measurement, it better captures the ground truth, it's useful as it gives you also ideally a breakdown of activities. So each machine deployed, how much CO₂ is producing, how much time was it working, and so on. However, there are also some constraints and limitations. For example, it's very expensive. It requires workforce engagement, either through direct cooperation. For example, they may need to stop the machines or alter their work patterns. And also it is time consuming, especially at the beginning. There is some software in the market that try to predict and understand life cycle assessments and emissions in construction, but all of them have the main limitation of only relying on historical data and no information on real time. This is something that even though for general assessment could be useful, if we try to reduce the CO2 and find direct intervention and means to improve may not be as reliable. Constraints when working on this are several. For example, there is no standardized protocols in literature when it comes to integrating construction 4.0 technologies in the CO2 monitoring. There is a high cost related to the use of sensors on a large scale, because each of them, of course, comes with the data subscription that you have to pay periodically, and so it may not be as easy to use for large-scale projects. There is also the fact that static emission factors, as the one, for example, cited by my colleague in the EcoInvent database, do not reflect the variation daily or weekly, which could be due to weather, energy prices, source of energy, and so on. Also, worker engagement is essential, and we have to find reasons for them to be interested in the project and comply. Also, external resources, for example, material transportation or production, are hard to consider. We know what is happening in the job site, but we don't know where do materials come from, how far they have traveled, and so on, which is also something that indirectly impacts the level of CO2 produced in the construction field. Recommendations given on this are, for example, to use IoT sensors to monitor on real-time data, adopt hybrid life cycle assessment, both top-down and bottom-up, so both process-based and item-based, to ensure precisions in emission measurements, track historical data to train models, use these models to predict and forecast future emission, and lastly, most important, if we want to actually see a change, visualize these results in a clear and understandable way for our stakeholders, which could be research, could be project managers, through KPI in dashboards. KPI, key performance indicators such as CO2 by hour consumed by each machine, idle percentage, how much time is required for each operation, and so on. Conclusions. Cyber-physical system represents a very good tool to integrate information from on-site data with the life cycle assessment, project status, or other kind of prior information, and it gives you a better tool to monitor and predict future CO2 emissions. Even though the cost to apply this is intense and there is no warranty of the results, the value that it produces is unmatched, and it's important if you want to see an actual change in processes. I will spend just a quick few words on our research. Since the submission of this conference paper, we actually produced a system that monitors CO2 tracking tracks CO2 in construction on a big construction site in Denmark using IoT sensors, and all of this data is being processed in real time using InfluxDB and Grafana, and all the results are shown. This is just research for now, but it's a way to show people how they can directly intervene in the construction site to reduce CO2 based on the activities being performed. This is the references, and thank you so much for the attention.